Oh, hey. Well, you guys caught me in the middle of something again. I'm just playing with this deck of cards. You want to pick a card, any card? How about the two of diamonds? Or perhaps you wanted to pick the Jack of Hearts. Do you guys think I'm crazy for playing with such big cards? Oh, you want a different deck, you say? How about this tiny little guy? Right? Bet you didn't know I had so many different sizes of decks, people. We are looking at conditional probability today, and this is page 18 of your probability packet. And I want you to take a look at the warm up question first because it's a great review of stuff we've been talking about for the last couple of days. So, I actually want to talk through this warm up with you because I want to offer up a new, possibly time saving strategy when you're just asked one question about rolling two dice and finding probabilities of certain sums. It says Jane rolls two standard dice. What's the probability? So she rolls the dice. What's the probability the sum is greater than 9 or less than 6? Or makes me think of add. So I've got to add the probabilities of all these cases, the greater than 9 sums and the less than 6 sums. I do want to emphasize that this is a great table to make. We've been making this table all along with numbers you could get on the first die, numbers you can get on the second die, and all the 36 possible outcomes for sums within the table. I especially love this table when I see a slew of questions about two dice. Like if I see I'm going to be asked 5 or 6 things about the sum on two dice, it's worth your time to just jot this table out for the outcomes. Then I can kind of add up the possibilities, right? I know there's 36 outcomes total. Whoops. 36 outcomes total. And I want the ones that are greater than 9 or less than 6. So greater than 9, that would be these 10s, 11s, and 12s. So 1, 2, 3, 4, 5, 6 outcomes that are greater than 9. Plus less than 6, so all the 5s, 4s, 3s, and 2s. So 4, 5s, 6, 7, 8. No, oh, I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You've got 10 of those. So out of the 36 outcomes, that's 16 for your probability, and you can reduce, make it, you have a 4 in 9 chance of this compound event occurring. All right, I'm pretty happy with that, but you saw how I fumbled around. First of all, this table took a long time to construct. Second of all, it was like I was just making sure I wasn't messing up counting all the numbers. I wonder if there's a more general table I could construct, and I'm just offering this up as a second option so we can look for some patterns. Can you make a little sideways t-chart here that has the sum on the two dice, so all the possible sums are going to go here. On the bottom, we're not going to show the actual ways to get it, but we're going to put the number of ways that you can get that sum. And this is a very quick table to construct. What are the possible sums if you roll two dice? So you could get the lowest sum ever, it could be a 2, and you can get all the sums all the way up through the highest sum. So you can get a 3, a 4 on two dice, 5, sum of 6, sum of 7, 8, 9, 10. You could get a sum of 11, and the highest sum you could possibly get is going to be a sum of 12. That would be 2 6s. Okay, number of ways to get that sum. We actually have a way to figure this out. How many ways can you get a 2 if you roll two dice? I feel like I only have one possible way. I've got to get snake eyes. I've got to get a 1 on the first die and a 1 on the second die. This table confirms that there's only 1 2 present. There's only one way to get it. Likewise, what if I went to the other far end, the other extreme of the table, and talked about sums of 12? How many ways can you get a sum of 12? There's only one way to do that. You have to get a 6 and a 6. Now let me creep inward on this table. Okay, so how many ways can I get a 3? Let me think of it. I could get a 2 and then a 1. Or, add this up, I could get a 1 and a 2. There are 2 ways that you can roll a 3 with 2 dice. Now let me go to the other end. What about an 11? How many ways can you get an 11? Well, you need big numbers for that. A 5 and a 6 would get you 11. A 6 and a 5 would get you 11. And I can't think of any other combinations of options on two dice. So this turns out to be a 2 as well. You're going to see some symmetry, some left-right symmetry in this table. So how many ways can you get a 4? Well, let's add them up. You could get a 1 and then a 3. You could get a 3 and then a 1. Or you could get 2 2s. I say that's only 3 ways, right? Getting 2 2s, you can't reorder it because you still got 2 2s. So there's 3 ways to get a 4. To get a 10, you get 5 and 5, 4 and 6, 6 and 4. I say 3 ways to get a 10. I can't think of any other outcome for 2 dice, and you'll see these 3s here. Now the pattern's starting to click. How many ways to get a 5? This should count up. There's 4 ways to get a 5. There's 5 ways to get a 6. We could list them out if we have more time. And there are 6 ways you can get a 7. Let me show that. You can get 4 and 3, 3 and 4, 2 and 5, 5 and 2, 6 and 1, 1 and 6. 6 ways you can get a 7. That's why they call it lucky number 7, because there are the most amount of ways that you can actually roll a 7. It has the highest probability of occurring as a sum. And then it counts back down. Should have this left-right symmetry. So 1, 2, 3, 4, 5, 6 counts down 5, 4 ways to get a 9. 3, 2, 1. So not too bad to list the numbers 2 through 12, and then we notice the pattern of how many ways it's happening. Now I can confirm that this 4/9 answer is correct. So as a second way to solve it, probability greater than 9 or less than 6. Well, here's all the sums that are greater than 9, these 3. All the sums that are less than 6. Here I'm just adding numbers. I'm adding 3, 2, and 1. And I'm adding 1, 2, 3, and 4. So if I add up all these and all those, I still get 16 ways out of 36. And that's going to be 4/9. So just to show you, there's another table out there. Now, today, we start talking about conditional probability. The probability that some event's going to happen given that, that's the key word, another event A has already occurred. We saw this with multiplication rule where we needed to kind of alter a probability when we had an and question given that another event already happened. So probability, this notation of B with a line and then an A, just to refresh, it means B happens, so B occurs, given that A occurred. Given that A already occurred. Like that with the line through it. And that's the probability of that happening. There is a good formula that we will continue to refer back to. Probability of B given A can be the probability that A and B happens divided by given that the probability of A having already happened. So it's probability of A and B occurring over just the probability of A. And I'll try to show you how that works. A lot of this is going to be common sense, which is good news. And lots of conditional probability problems lend themselves nicely to tables. So here is a table of a test that somebody did. I'm just going to add an extra column and row for totals here and here. And we'll show how that's used in a second. So let's read the table. They must have tested, I guess, 99 women. And since pregnancy tests aren't foolproof, sometimes you get indicated positive when you're not actually pregnant. So you got a positive test result. And for 3 of those women, they actually weren't pregnant. Versus other times, you might get a negative test result and you actually are pregnant. For these 5 women, they were pregnant, but the test actually came back negative. So step 1, when I see a table and some questions underneath, is I'm going to get totals for all the columns and totals for all the rows. So positive test results, there were 83 total women that got a positive test result out of the 99, and there were 16 that got a negative that did this study. Going across, there were 85 women in the study who were actually pregnant, and then 11 plus 3, there are 14 women in the study who were actually not pregnant. If I add this column, I get 99, the number I was expecting. Also, if I add this row, the 83 plus 16, I get the 99 total subjects in the study. The first 2 questions, let's see, one of the subjects is randomly selected. Find the probability just that the person tested positive for pregnancy. Let's get our feet wet. If you want to try A and B on your own and pause the video and then come back, I'll go over A and B with you. Those are 2 good ones to start with. So you're just finding probability. You pick a random person from the study and they tested positive. I'll put POS. Well, how many tested positive? Let's look at our totals. Positive test result, there were 83 of those. So the chances are 83 of them were testing positive. Out of the 99 that you had to choose from, there is going to be your probability. So 83 over 99. With a lot of these, it's fine to type it in and get a nearest thousandth decimal. You have an 83.8% chance you're picking someone who tested positive. Now, if one of the subjects is randomly selected, find the probability she was actually pregnant. So this is P, pregnant. Well, how many were pregnant? Subject is pregnant. That was 85, slightly more out of the 99 total. So 85 over 99 is a good way to leave it. Typing it in, you have about a 0.849 chance of picking someone who is actually pregnant, slightly higher. Now the conditional probabilities. Let's circle C and D. If a subject was randomly selected, find the probability the person tested positive. So here's how you'd write it in our notation: positive, given that she was pregnant. So this is what the company that makes the test wants. Given that they're actually pregnant, they want the test to come up positive. Now you'll see that our denominator gets slightly altered. Up top, the formula said probability, or number of subjects that are pregnant and positive, A and B, divided by just the pool of people who are pregnant. So given that she's pregnant, that limits us to the total amount of women that were actually pregnant. So there are subjects is pregnant, there are 85 of those. That's your denominator, all the women who are pregnant. Positive given pregnant, well, that's positive and pregnant. There's 80 subjects that were positive and pregnant. 80 over 85 is a great answer for that one. And we can make this, I'm bouncing around here. Okay, so we can make this 80 over 85, that's 16 over 17 when reduced, so that's a better way to leave it. And then as a decimal, we've got 0.941. So a 94% chance the test is doing what the company wants it to do. If one person's randomly selected, find the probability she was, now let's switch it up, pregnant, given that she tested positive. Okay, now you've got a new denominator. You're only choosing from the total that tested positive, and just to refresh, total positive test results, there are 83 of those. Pregnant and positive, we put that numerator in the last question. There's 80 of those out of the 83 that tested positive. So 80 out of 83 is fine, or a 0.964. So 0.964 chance, roughly. Subject is negative given not pregnant. I mean, this is something that the company wants too. If they're not pregnant, they want the test to come up negative. So let's see what our numerator and denominator would be. And I guess I don't have to rewrite that. For this one, you're going to have the not pregnant, what you're given, total at the bottom. So not pregnant, there was 14 of those. Out of those 14, if I look back up at the table, 11 of those, almost all of them, but not quite, came up with a negative test. So a slight room for error there. 11/14, roughly a 78% chance or 79% chance, 0.786. And then the last one on the page, find the probability not pregnant given negative. Well, here's your denominator, all the tests that came up negative. So tested negative, there's 16 of those. And not pregnant, there are 11 of those that are not pregnant and tested negative. So 16 total that tested negative, 11 that are not pregnant and negative. And that gives you a decimal of about 0.6875. And actually, that's exactly 0.6875, or 0.688 if you round it. All right, as you turn the page to page 19, you'll see all over this page just a couple more examples of good practice of finding conditional probabilities from tables. Some of this I want you to try on your own, but number 2 we'll walk through together. You might want to pause the video now and use my advice from the first problem. Total up the columns, get total numbers beneath, total up the rows. This is especially helpful if you see there's going to be 4 or 5 questions about a given table. Chances are you'll need some of these numbers. And this column adds up to 17,472, and this row also adds up to 17,472. Those should both check out. Total subjects in the study. You pick a student at random from this table. What's the probability they're a female given that their type of school is graduate school? Well, if their type of school is graduate school, we're not talking about all the 17,000 people. We're just talking about the total 3,303 students that are in graduate school. Females in graduate school, there's 1,954 of those. So there's your numerator. Big, huge fractions like these are just big numbers here. I prefer to see the decimal answer. So for this one, let's round it nearest thousandth, 0.592. And check me on that too. Probability of female. This one's not conditional. Just what are the odds? You go into this pool and you pick a random female. Well, since there's no condition, I'm saying we're picking from all the 17,472 people. And how many females are there? Let's go to the total of the female column, 9,933. Okay, rounded, you might get a 0.569. What's the probability they go to a 4-year college given that they're a male? Given they're a male, I go to that first, do total of males, 7,539 from that column. 4-year college, you would say 4,324, and that'll round to 0.574. Okay, keep on going through the page. It's going to be really good practice, and stay tuned for next time when we continue talking about conditional probability.